in 52, specifically A, we're looking at trying to produce this molecule from butadiene and ethene. It's probably most useful to think about this backwards and think about what types of reactions could give us this. Because we're in the chapter that's mostly on pericyclic reactions, we should think about these as probably being the focus. Whenever we see a cyclohexene, that's a pretty good indication that we have some sort of Diels-Alder type reaction that could have formed that cyclohexene. In this case, if we had this cyclohexene formed, the reverse Diels-Alder would have us putting electrons back like this, and this, and this, and we'd actually be having a butadiene, which is one of the types of things that we want to form, or use as a reactant rather, and a cyclohexene to begin with, reacting to make this new adduct. So that gives us one reaction that could happen. We could have a Diels-Alder reaction that would bring us to the final product if we had cyclohexene. So the question is, how do we make the cyclohexene now if we have a butadiene can react with it and form this? Cyclohexene is the simplest Diels-Alder that we talked about. It has the butadiene and the ethene as the two reactants. And so to go up to the cyclohexene, we just have to heat up butadiene and ethene. That gives us this piece, and when we heat it up with butadiene again, we can get this second addition type reaction. And the mechanism for this going this way would be we'd have these move over to a new bond here, we'd have these move over to a new bond here, and these move into the backbone. So you have a double bond here, which we see here. We have a new single bond here and here, which we see in both of those cases. Notice the mechanism is almost identical to what we see here. New sigma bonds between the alkene pieces, and at the backbone we have a new double bond between where we had the diene double bonds before.